What's up, everybody? Thanks for being here at Miss Transform 4. And today we're continuing to work on algebra functions, representing functions, and domain and range. So hopefully you've already watched my functions versus relations video. Plus I got a bunch of gold from a couple years ago. Go check that out. But today we're going to focus on mainly looking at how to represent a function as a set of ordered pairs, verbal table, mapping, graph. Bunch of different ways to represent your functions or a relation. Identify domain and range. Identify independent and dependent variables. So at the end of this video, hopefully you know how to do all those things. Definitely take some notes on those things specifically. So represent, identify, that's our big theme. Domain and range correlates to your x and y, and all relations relate the set of inputs to the set of outputs. So every input gets mapped to a specific output or output. It doesn't have to be specific necessarily in the case of a relation, but the x value, which represents your input, which represents your domain value, which represents your independent variable. So make sure you have that word association between all of those. They do what they want, INDEPENDENT, I don't know if you know what that is. You might be too young for that. But you're independent. You do what you want. You work on your own schedule. In life, what's independent? Time. Time's going to keep ticking. Like the timer on this video is ticking, no matter if I'm talking or not. Generally, time is always a great example. Days, hours, minutes, number of hours worked, number of people surveyed compared to number of yeses. Anything that does its own thing is independent. And then you have your outputs, which are your y's, your range value, your dependent variable. Those values only change and only can change when the x value changes. That's why they're dependent. A lot of y'all are dependent on your families and your adults because you can't do things without them. Hopefully you're setting yourself up to be independent as you become an adult. When you're dependent, such as the amount of money you're going to get paid on your paycheck is dependent on the number of hours that you work. The snack you get out of the vending machine is going to be dependent on the button that you press. The distance that you travel is going to be dependent on how long you travel or how fast you're going. The Cannon Man, the height of the Cannon Man is going to be dependent on how long he's been flying in the air out of the cannon. Lots of different ways to associate that. So here's just another way, a bunch of examples, get that association. You definitely don't want to be mixing up x and y, because if you're getting x and y mixed up, input, output, domain, and range, you're going to be lost as it is. So make sure that you have these examples. Sound good? So representation. So I mentioned play-doh. I consider functions like play-doh. You can represent them in all different ways. It doesn't change what you're looking at. It doesn't change the data set. It doesn't change the points. You just can show it in many different ways. And this is one of the reasons why I love functions, because some people prefer to be visual and look at graphs. Some people can understand something off of just verbal context. Some people want the function notation. Some people want the mapping or the table. You do you. That's what I'm trying to get at. You have to make sure, though, that whatever you do, it does show that relationship between the domain and range. Like if you're not showing how the domain and range, the x and the y are related, are connected, you're not showing the function. So make sure that you set it up correctly. So here's an example of a bunch of examples. If you're given a set of ordered pairs, or let's say you start with a function notation, and I will have a separate video on what function notation is and how to use it. But a function notation is f of x equals 20x minus 10. So this equation basically says if you put an x into this function, if you put in an input, what we're going to do is we're going to times that input by 20 and then subtract 10. So maybe that doesn't tell us a lot of what that means, but then you look at the verbal, and this is why the verbal is important, because it's how you deal with real world contextual problems. You're going to make 20 bucks an hour raking. Maybe I'm hiring rakers. Do some leaf removal. But I don't have time to go to the store and get you a rake. So I'm like, all right, I'll hire you. I'll get you the jobs. I'll tell you where to go, but you need to get a rake, and the rakes are $10 at the store. So you get yourself a $10 rake. You go work. How do you know what you're gonna make? Well, you plug in different numbers of hours, and you can see we did that in the table. If you just buy the rake and don't work, well, you're negative $10. And then every hour that you work after that, the Y value, the output increases by 20. So up by 20, up by 20. That's something called the common difference, by the way. Up by 20, up by 20, up by 20. So if we look at it like this, and I'm dropping this gem in here for when we get into linear equations later, plus 20, plus 20, plus 20. So that's your change in Y, and I'm just going to drop that in there. I do not expect you to know what that is yet. But then we can look at the change in X also and see, oh, we're changing by 1, we're changing by 1, we're changing by 1. So for every 1, the X changes, the Y increases by 20. For every 20, the Y increases, the X increases by 20. So that's some bonus math for y'all today. You can see on this graph, and I know it's just kind of ugly and it's not labeled, but look, there's 1, and there's 2, and there's 3, and there's 10, and there's negative 10, and there's 30. That what you do is you plot, and remember it's X comma Y, right? And X is your horizontal axis, and Y is your vertical axis, and you plot the X, you find the X, so at 0, the Y is negative 10. For Y, at 1, the Y is 10, and at 2, the Y is 30, and if you had a different graph, or if you scaled this differently, you can put more and more points on it. And lastly, we have a mapping. Mappings and tables are very similar. When you're working with a clean data set, like this is a linear example as a constant rate of change, tables work fine. But if you're dealing with something that's not so clean, that maybe isn't a function, you might like a mapping. Mappings just show the way a little differently, and if we had an X that went to multiple Y's, or if we had X's that went to the same Y, a mapping might be a little cleaner. And then we have the set of ordered pairs, so just the ordered pairs, the points. And again, we stopped at 3, 50, but you could have kept going to 470, 590, etc., etc. So I would personally put all these examples down as an example of one function and talk about the differences, the benefits of how you use each of these, because all of these representations have their place in your toolbox. So, domain and range, right? We know that this is the X and the Y, the independent, the input and output. We've been drilling in, we've been working on that word association. But we want to be able to talk about possible domain and range, or what the actual domain and range is. So you need to list it out. So when you're given a set of ordered pairs, right, you know that these are all X comma Y's. X comma Y, so you have all our X's, and you have all your Y's. And that's literally all I need you to do. Now, in this case, right, we use the 3 dots to show that it can keep going, because this is not a closed set of data. It can keep going for every hour that you work. We have set notation, make sure you not use that. And then to get a little fancier, and this ties to continuous functions, both of these, set notation and interval notation, carry on to other maths. So you want to make sure that you kind of get your head wrapped around this. So interval notation, you can use, this format, or this format, or this format, or this format. And when you do this, what you're looking at, what you're actually getting, is a way to represent all the X's and all the Y's without listing them all. And that's nice, right? Because some values go on and on and on, and you don't want to write 1,000 numbers. So when you use the closed bracket, that means that the endpoint's included. So think about like a closed circle and inequalities. We're saying that we do touch that number, that is included in the data set. And when you use this, it's a soft bracket. It means that that's not included. So if you look at the domain in this situation, we start at 0 because 0 is the lowest, the least value X, and it can go all the way to infinity. I mean, realistically, probably not, right? So, and that's something that I really like about this, is there's non-contextual math problems, and then there's real life problems. So in this situation, we're talking about you raking there's a limited number of hours you can rake in a day, in a week, in a month, in a, people don't want their leaves raked all year round. So there would actually be a hard cap on this that you could try to figure out. And that would be a really good practice. So, but just for argument's sake, let's just go pretend this is a non-contextual issue right here. We use the hard bracket on 0 because you could have 0 hours. Now that'd be foolish, but in this situation, but you could. And we go all the way to infinity. Another way to write this, and I didn't because it doesn't show up when I type it properly, but you could make it look like that. Good old infinity sign. Or Batman eyes. Spider-Man eyes. Superhero eyes? I don't know. My middle child's obsessed with the Spider-Verse movie. We've been watching it a lot, and I'm here for it. And in this case, we have -10 is the lowest possible y value, and then it can go all the way to infinity. We use soft bracket because you can't actually touch infinity. Ask Buzz Lightyear. He's never been there yet. He's been beyond it, but he hasn't been there. So, a little bit of practice for you. I personally would pause this right now. Do your thing. Maybe you're like, I ain't coming for practice, Mr. Hansen, 414, see ya, bye. Hit that subscribe button on your way out and like the video, but whatever. But you might want to take a look at this. So, I already did it for you. You look at the x's, you look at the y's. You get the x's, you get the y's. And it's good practice to write your domain and range in ascending order, so smallest to greatest, least to greatest. And then on this mapping, you would only write each value once, so you got multiple, -5s, technically, right? And this applies for everything, tables, graphs. Just write it once. Don't write the same number twice in the domain or the range. Maybe you start a little, art business, which I know I got a lot of talented artists that I've had over the years. 0 to infinity, again, contextual. Maybe you can only make one piece of art every 2 hours. I don't know. So there's a cap if we're talking about a specific time frame. And the money that you would make, the range. So domain is the number of arts, and the range is the money for your arts. The money you make depends on the number of arts you make and sell, because you're not done making your money, so you actually go through with it. So functions, relations, hopefully you have understood how to represent functions in multiple ways. You understand what this concept domain and range, interval notation, set notation, just trying to make sure we hit everything. Independent variables. You should be feeling pretty good. So hit that subscribe button, hit that like button, get somebody else that needs some math help over here, and I'll see y'all later.